Welcome to tutorial 4 in Methods, Transportation, Econometrics and Statistics for the master course. We have two problems here. The first problem, 4.1, is on fitting elephants. We do not want to fit this elephant really, but we will see how the title of this problem comes from. So first we have given a very simple set of data. So the exogenous variable is just a single. Obviously it's sort of increasing from 1 to 6, and the endogenous is also increasing. Of course this can be ordered as at will, but it seems that there is a tendency of increasing. So if x increases, also y increases. First we consider a case without this gray point, which will be needed later. So we come to also to two models. We will discuss two models, two candidates. Model 1 is a simple linear regression, y equals a plus b x plus epsilon, and M2 is model 2 is a polynomial regression of fifth order, which has 6 model parameters from beta 0 to beta 5, 0, 1, 2, 3, 4, 5, 6 variables. So first, are these models linear, parameter linear, or non-linear? They are not strictly linear because in the exogenous variables x, but they are linear in the factors x to the power j. So in this sense, they are parameter linear with respect to the original exogenous variable, and linear with respect to the new factors. X to the power 0, that is the intercept, x to the power 1, and then we are done with this model, and in the model M2 we have 4 other factors, x squared till x to the power of 5. That was point A. Point B, check if these models are well specified with the data. From the first from the data from the model specification, both seem to be well specified because the different factors were constant, x to the 0, x to the power 1, linear, squared. These are all independent functions, so it seems that there's no problem with dependency. However, statistically nothing can be said. If you look at the curves, so sometimes it's above, sometimes below. The statistical specification seems also to be correct. However, the data specification is only correct for the first one, because first one has 2 parameters. We have 6 data points. That is of course a very small sample, but the model is correctly specified because there are more data points than parameters. However, this is not the case for the second model. We have 6 parameters and 6 data points. So this is a misspecification. You cannot do any statistic with this model. So it's the Gauss-Markov condition number of data points is not given. Now the ordinary least squared estimators of two models. You can still estimate this model. However, you will get a residual error of exactly 0. Why is this? Because we have 6 unknowns and 6 equations. So we can just solve this and get an exact fit. So the fit is exact, but still the model is not very good. Here the fit is not exact because there are some residual errors. And the reason why the fit is not, this model is qualitatively good and this not, although the fit here is 0, the residual error is 0 and here it's not, is just that obviously if we add another data point, it will, because these points are scattered about some linear, it will, in most cases, that of course it can also be different, but in most cases it will be somewhere also that will not violate this increasing tendency of the data points. If it does, it is even it's probably an outlier. So if we insert this point as a sort of validation, we will get also for the validated model with a new data point, we get a small sum of squared errors. It's completely different here because polynomial of high orders tend to swing a lot, fluctuate a lot, and here we get a huge residual error. So in fact, with this new data point, the residual error, sum of squared errors of this is much higher than this. Also, this has less parameters. So we also learned in the lesson 4 about model selection schemes, for example, Akaike or Bayes selection criterion. And here, if we only had the choice between this and this model, this would definitely be preferred. Maybe even a squared model, but not more. And so what's the elephant? Because that's some saying is with 4 parameters you can fit an elephant, and with 5 you can fit the wiggling of its trunk or tail. And here it's quite literally 5 parameters are too much for this small data set, having only one real exogenous factors. We come to the second problem, 4.2, regression including qualitative variables. So let's look at this table for a situation regarding the average speed of trains as a function of a year since 1900. That means that's more than a century ago, and this is year 2000 because our indicator for year is just the year minus 1900. Then we have a train category, and that is the mentioned qualitative exogenous variables. There are local trains and there are fast trains, for example intercities. And the endogenous variable here is the average speed. That means the speed including stops at the station, which increases over time and also is faster in intercities versus local trains. We use following model. The average speed y is a constant plus linear increase with a year, and here with x2 we need to we cannot simply insert L or IC because these are qualitative variables, nominal scaled, and you cannot add L with some number as a year, for example. But we will come to that later. So first, the functional specification. So the scaling of the exogenous and endogenous variable. So years obviously metric scaled. It's real valued, or discrete if you only distinguish integer years. This is nominally or qualitatively scaled, and speed of course is a metric variable. So that's the scaling. Does the model contain superfluous or a missing exogenous variable? Obviously no superfluous variable. Obviously the year matters because the speed increases, and obviously also the train category matters. But maybe there are some other missing variables, for example the country or also the density of stations. If there are many stations, then of course the average speed will be lower. But basically this is a correct specification regarding to the functional specification. What about structural change? There may be one, because obviously in the beginning 0, 30, 60, 0 and 30 were only with local trains, and only 60 and above there are also intercities, or the precursors of intercities. I don't know if they are called this in the 1960, probably not, because such an anglicism in Germany is not used at this time. But anyway, up to the year 1960 we have 2 categories, and before we have only 1. So maybe there is some structural change which would require an additional dummy, but there is no further evidence for that. So that was task A. Now we come to task B. Check the data specification for correctness. So how many data points do we have? 1, 2, 3, 4, 5, 6, 7, 8 data points, and we have 3 parameters, beta 0, beta 1, and beta 2. That means there are a sufficient number of data points, so we have 5 degrees of freedom left once we have estimated these 3 parameters. Is there multicollinearity? Of course, there is some correlation. For example, the speed with time, the year increasing, and the train category at the beginning were only low speed trains, and then there are intercities and low speed or local trains, but with no perfect correlation. So regarding multicollinearity, there is no problem. Sufficient data points, and our exogenous variables deterministic and measurable. Time is of course deterministic, and the train category is also clearly deterministic and observable, that means measurable. So this is the model specification is satisfied with the exception of the requirement for linear factors. And that's where we treat with x2. So this x2 has only 2 values. It can, x2 was a train category, it can be either a low speed or local train, or it can be a fast train and intercity. And that we need to code with some number. We need a number because these are real valued numbers, and in order to add this must be also some real valued number. So this is real valued, and this is we need some dummy where we can do arithmetic with, and in the simplest case is just 0 for slow regional trains and 1 for the faster ICs. We could also do it the other way around, it doesn't matter. It only matters that once we took the decision, we need to stick for it in the interpretation. So now we have fully specified the model, and also this factor is linear because it's either 0 or 1. So what is the meaning of the parameters? Beta 0 is the intercept. Does it have a meaning? In this case, it in fact has, because we have y equals beta 0. If the statistic, the random term is 0 and on average it is 0, and if this exogenous variable x1 is 0, which year does it mean? It's the year 1900, because that's how we defined x1. And also, if the dummy is 0, that means beta 0 is the expected speed for low speed trains in the year 1900. So we expect it to be a positive quantity, and in fact if we're looking forward 42.2 km per hour, so this has also a plausible value. Now to the next variable, beta 1, that is the increase with time. So obviously beta 1 has the meaning increase in kilometer hours per year of the expected speed. So it should have a small positive value, and in fact it has. So it's nearly half a kilometer per hour per year trains became faster in the last century, from 1900 to 2000. The last is the dummy, a parameter for the dummy. So obviously the dummy is 1 if it's an IC, and it's 0 if it's a slow train. So this beta should be positive, because it just gives indicates for a given year the expected speed difference between fast and slow trains, and in fact it is 28.2. So it's that means on average the intercities are nearly 30 kilometers per hour faster than the local trains. So now we are finished with C. Now we come to the quantitative part. here we assume that we already have calculated the ordinary least squared estimators by some statistic programs. We get these values, and also we get this estimated variance of covariance matrix. Diagonals are, as always, the variances of beta 0, 1, and 2, and these are the covariances. Here all the covariances are negative, but that's just by chance. So give a forecast for the expected speeds for the slow and fast train category in 2020. Obviously we need to insert for the variable x1 the year the value 120, because 2020 minus 1900 is 120, so x1 equals 120, and for x2 we either insert 0 or 1. So for the slow trains we have just this constant, then 120 times beta 1, and no beta 2 because the dummy for slow trains is 0, so 99.1 kilometer is the expected speed. For fast trains just the dummy is added, so that is the beta 2 is added, so we have 127, which is a plausible value. So we source D. Now we come to E, do some inferential statistics. So in D we have made a forecast, but now we would like to know what is the error, expected error of this forecast. And that means the forecast is of course either is beta 0 plus 120 beta 1 or beta 0 plus 120 beta 1 plus beta 2. So in order to calculate the variance of this estimator for future speed, we need general formulas for the variance of a linear combination of correlated random variables. And basically, let's assume we have here a general linear combination of two random variables x and y with some non-random real valued prefactors a and b. Then the expectation is, as a linear operator, you can just pull the expectation operator directly to the statistic random variables. So we have this and this. Variance is a quadratic quantity, and you can only pull into if squaring the prefactor. It means the diagonal terms of a variance covariance give this term a squared and b squared times the respective variances of x and y. But we also need the non-diagonal covariance variance term, which is just in this case 2ab times the covariance. And now we apply this general formula to our case. Exogenous factors x0 is 1, x1 and x2. So expectation is just the estimator is unbiased, so the expectation is unbiased. Interesting is the variance. So first we have the diagonal elements. That's the sum of xj squared times the variance of a beta j. And then we have also the sum of all non-diagonal terms. And because we are symmetric, we can only use the upper triangular non-diagonal terms times a factor of 2. So this is a special case for just two variables. Now we can specialize it to the two predictions. So first for the slower trains, this is the linear combination, that's of beta 0 and 120 beta 2. The variance gives 1 times the variance of a beta 0, then 120 squared times the variance of beta 1, 1, and 2 times the covariance. And this gives this term. In 2020 we have 3 terms. So the diagonal is variance of a beta 0, 120 squared variance of beta 1, and 1 times beta variance of beta 2, and then the 3 covariance terms, the 3 non-diagonal terms, or the 6 terms, but with a 3 multiplied with 2 because of the symmetry, and this gives this value. Interestingly, because of the negative correlations, adding some additional term reduces here even the variance. We can also show it by graphics. So this is the slower term. So this light blue limits just give the limits of the 1 plus minus 1 sigma of the estimator for the slow trains. So you see this mentioned hyperbola shape. The error is the smallest at the expectation value, which is here 90/60, and the same, we have the same here for the faster trains. So that was question C. Question E. Now we come to question F. Calculate the confidence interval of beta 1 at a significance level alpha equal 5%. So we just can use the standard formula for confidence interval. It's symmetric around the estimator at beta 1, and because we can only estimate the variance, the residual variance, and that also means the variance of the data estimators. The relative deviation, so the deviation of this expectation is student t distributed if we express it in terms of a expected standard deviation. So we have just the standard formula for the confidence interval. Basically the confidence interval, we need this half width of a confidence interval. This is just the standard deviation times the corresponding quantile of the student t distribution with the 5 remaining degrees of freedom. We already mentioned that. So we need to calculate this quantile. This is just tabulated, giving this value 2.57, and we need to calculate this. So this is just it's the diagonal square root of a diagonal term of the variance covariance matrix of 1, 1. However, watch out that 1, 1 is not the first element but the second, because the indices start with v0, 0 for the intercept beta 0. So if we do the math, the square root is 1.102, and this, then we get the half width of 0.262, and that means the confidence interval of a beta 1 is between 0.21 and 0.74. So it is, in particular, it is positive. So 0 is not contained in this confidence interval. So we also know that a symmetric test of a point null hypothesis beta 1 equals 0 could be rejected. So now the question G. The above model, it means this model, does not reflect changes in the different changing rates for fast and slow trains. Now we want to modify the model that also different rates in accelerating will be considered. Now if we have a common rate of increasing speed, we have this beta 1, but if we have two different rates, we need to take a separate value of beta 1 if the x2 equals 0, if it's a 1. That means we need to interact with x1 with x2, and this could look like this if we do it by hand. So first the constant remains as is, then here we have the acceleration rate in time for the slow speeds, because it's only 1 if x2 is equals 0 and 0 if x2 equals 1. Then here we have beta 2 is now a new rate of acceleration in time for the faster trains, and this is the beta 3 is the parameter for the dummy. We can also write it in this term, because x2 can only take on the values 1 and 0. So this case condition can also be written as 1 minus x2, and this as x2 itself. And then we have, so this is the same, the meaning, beta 0 is unchanged, beta 1 is changing rate of the slower speed, beta 2 of the fast speed, and beta 3 is the difference between the faster and slower trains in speed and in 1900, because the rates may, if the rates are divergent, the speed difference can also become larger or smaller. And finally, we can also simplify the specification by reformulate the interaction term just as a product, not as here where we have two products. Then the the beta change the meaning. So with beta 0, beta 1 and beta 3 is unchanged. However, with beta 2 has now the meaning that the difference in the speed changing rates with time between the fast and slow trains over time. So now we come to our last question. Now we again consider as the equal changing rate of speeds with time for the slow and fast trains. However, we now consider a third train category. So besides the local trains and the intercities, we also have intercity expresses. So that's the slow speed, the fast speed, and the ultra fast speed. And now we should change the functional specification of the original model, that means this model, in order to do that. Here again we have the qualitative variable x2 can now take on not only two values, local and intercity, but three values, local, intercity and intercity express. Again, we need to transform it into numbers, and because we have three values, we need two dummies. The general principle is if you have a nominal or qualitative variable taking on m values, you need m minus 1 dummies with values 0 and 1, and the one value which does not get per dummy is the so-called reference value. So here we had two values and one dummy. Now we have three values, and therefore we need two dummies. So this can look like this. So constant, that is just the changing rate for speed with time, which is common for all three types. And here we have a dummy delta x2, and delta x2 means it takes on the value 1 if if it's an IC, and 0 otherwise. That means this dummy is 0 if the category is either local or ICE, and here we have another dummy which is only 1 if it's an ICE, and 0 if we have IC or slow speed. And then obviously with beta 2 is the difference in speed, the expectation between ICs and the reference, which is the local train, and this is the difference between ICE and the local train. Yes, that was tutorial number 4. Many thanks for listening.